Hi, good evening. Um, let me say this first. I am going to post, I think I mentioned this last night, I am going to post the videos of these lectures. My pre-recorded lectures will probably stay on YouTube, but these videos, I will remove after this course, um, so that you don't feel like your questions asked in class will be preserved for all time. I suppose someone could download them in the next 6 weeks, but that's unlikely. Um, but if you are uncomfortable showing up in that way, you can chat to me, and that would be fine too. I'll try to keep an eye on it. Um, Beth is here too. She might help me out that way. Not what I wanted. Also not what I wanted. Okay. So let me start class by asking, are there any questions? That is a no. Great. Okay. um, so let's just start in. So there were three pre-lecture videos for tonight. They were, let's see if I can find it here. Motion graphs, I think. What is my motion graphs? Yeah, acceleration and free fall. The free fall video, I intended to put a link to another video in it. I did ultimately end up adding that link. I forgot to add it originally. I added it as a card, which I didn't know was a thing until today. So learning YouTube, it's great. So if you didn't see that video, it's not a big deal. You could go check it out after this lecture. It's a beefier version of a demo I like to do in person, but I don't have that stuff with me in my basement. So let's just launch into it. So I'm going to load screen mirroring and share this screen with you. Come on. Okay. So I want to talk about motion graphs. I plotted some of this stuff here. So come on, man. We can do this. That's fine. We'll just do this. So position versus time is just another way to represent motion, right? I mentioned that the slope of position versus time is velocity, right? You can define, if you define slope is rise over run, and you plug in what those definitions are, right? The rise is literally motion on the x-axis, which is vertical here, which is a little weird. And run is motion on the x-axis, which is time, right? So delta x over delta t, that is velocity. And let me be clear here. That's technically average velocity, but if the velocity is constant, the average and the actual velocity are the same, right? Not what I wanted. We can also plot velocity versus time, and here you can definitely see, oh yeah, those velocities were constant, right? Because these are flat lines, right? Because the slope in these three regions really were, I will get used to this, I promise. They really were like something medium, something small, and something bigger. And that's what's happening here is medium, small, and bigger. Let me mention, because I didn't mention it in, I think I didn't mention it in the video, that from going from position to velocity, right, we took the, I did mention it in the next video, we took the slope, right? But if I want to go backwards, if I want to go from velocity to position, I can use an area, right? You can see that pretty quickly if I do this. Let's take the area of, I don't know, this section. Let's do this section. So if I take the area of this, yes, I'm going to scribble all the way over there. Marvelous. If I take the area of that, right, how do I calculate area? Well, it's length times width. So let's label them. So here's a, I don't know, a width, and here's a length. That length is a, this is a time axis. So that length is a delta t. And the height of this is that velocity, right? So if I say v times delta t, well, what is that? What is v times delta t? If I remember that v is delta x over delta t, I can say delta x over delta t, running out of space. Haha, no, I'm not. Delta x over delta v, that's, sorry, delta t, that's the definition of velocity or average velocity, times delta t, that really is delta x. So I see mathematically this area, right, because that was area, length times width here, is displacement, right? So going one direction, and I think this is actually at the beginning of the handout when you go to here. Area under the curve for a velocity versus time is displacement, just like slope of position versus time is velocity. So this is an algebra-based course, but if you've ever had calculus, the word derivative and integral may come to mind. That's exactly what we're doing here. The relationship between these are those relationships. Okay, so I want to do a couple examples here. So let me. Oh, you guys, were you not able to see any of what I just drew?
We saw it.
Oh, good. Good. Thank you. I forgot that I'd moved. I was looking at this screen and not that screen. I'm confusing myself. So let's do this example. So below is a motion diagram for a car moving along a straight stretch of road. Which of the following velocity versus time graphs matches that motion? So what I'm going to do is start a poll, if I'm able to. I wonder if I can do that while I'm sharing my screen. Nope. Where are the controls? Meeting controls. Ah, yes. Okay, I found it. All right. So here's a poll. So which of the following velocity versus time graphs matches this motion? So what do we have? We have, looks like two distinct velocities, right? We've got a region where the dots are close together and a region where the dots are far apart. Looks like that's, it's two distinct ones, and it's not like speeding up or slowing down through the whole motion. So I would call this slow but constant. Constant. And I would call the other one fast and constant. I can't write with an eraser. This one's fast, constant. By the way, I'm not going to use your answer for any kind of grade. This is mostly because I just learned about the polling tool and I thought it would be cool. So the correct answer should be C. Right? Why is it C? Because this is two constant velocities, right? It's tempting to say, what's definitely not that one. Something fell, but it didn't break, so we're good. Not this one, because this is zero velocity, and there's no zero velocity here. These two both have increasing velocities, right? They start at zero and they get bigger. It's tempting to say it's this one because this has two distinct regions and one is bigger than the other. But this is the right answer. Does that make sense to you guys? Questions about that? Moving on. No, I want to do this here. Example 8. A graph of position versus time for a basketball player moving down the court looks like this. which of these velocity versus times matches that position versus time? I'll start the poll. So remember the relationship here, that velocity is slope of x versus t. Slope. Okay. So if position isn't changing, velocity is 0, right? So in this region, v equals 0. In this region, v is constant and negative. Right? So I'm looking for one of these that is 0 at the beginning. So that's these three, right? Because this one starts with a positive velocity, and that's not what this plot does. So it's got to be B, C, or D. And it looks like I've got two distinct velocities. One is 0, and then one is negative. So it's not this one, because that goes positive. And the velocity is constant. It's not increasing or decreasing. So it's not this one. It's got to be this one. You guys buy that? Again, I'll ask other questions. Where are my chats? Here, make sure nobody's asking. No. Okay, cool. All right, we'll do one more. So here's going the other way. Here's a velocity versus time. The graph of a hockey puck shot into a goal. Looks like this. Polls. End the polling. No. Yes. Okay. So there's velocity versus time. Looks like it's positive and constant, and then 0. Right? So constant and positive, and then 0. That's V. Ooh, that's my slope. Sorry, that's not the slope, right? That's what the velocity is literally doing. So how do we go from V to X? Remember that it's area. Okay. That's not super helpful. Maybe it is. Maybe you can visualize it that way, but you know what? I would rather think about the slope relationship. So I'm looking for something with a positive slope and then 0 slope. Okay, I'm gonna switch back to red so we can cross off the ones that aren't true. Something with a positive slope and then 0 slope. Well, A and C both have 0 slope to start, so that's not gonna fly. That doesn't work. So it's gotta be B or D. So picture what's going on here, right? In B, we're starting at the origin. We're moving in the X direction in time. And then at this point where velocity goes from positive to 0, we're moving back to the origin. X goes back to 0. Instantaneously, right? Is that what hockey pucks do? Maybe, if you have a Stargate. No, that's non-physical, right? The position versus time needs to be a continuous plot, right? So that can't be it. So D is what's going on, right? The hockey puck is moving in the positive X direction, and then it stops, meaning X doesn't change anymore. Does that make sense? I will take your silence as a resounding yes. Which is funny, because last time I took your silence as a resounding no. It's great. I can make silence mean whatever I want it to mean. Maybe later, you guys. Okay. Seriously, though, you guys are good? No questions?
Yeah.
Okay, awesome. That's fabulous. Let's keep moving. Let's do example number 10. 10 is a pretty simple problem, but what I want to introduce with this problem is a problem-solving scheme, okay? Example number 10 says, a soccer player is 15 meters from her opponent's goal. She kicks the ball. After half a second, it flies past the defender who stands 5 meters away and continues toward the goal. How much time does the goalie have to move into position from the moment the ball left the kicker's foot? Okay. So I'm going to suggest we start by drawing a picture. Right? So what is the picture I'm going to draw? Well, you have to start with a soccer player. How do you know that's a soccer player? Because there's a soccer ball right there, obviously. How do you draw a soccer? Oh, perfect. Okay. Great. I'm not an artist, you guys. But it doesn't matter. The picture just has to help you visualize what's going on. So she kicks this ball. Right? There's a defender right here with a fairly long neck, 5 meters away. And then a goal. Oh man, how do you draw a goal? It's like a net. 15 meters away. Not quite to scale. Ooh, but you know what? That's a little more to scale. Great. And, you know, there's a defender, or sorry, the goalie right here. So the question is, how much time does it take to get to the goal? Okay, so we drew a picture. Let's gather some information, right? So that's maybe our second step. By the way, I'm kind of following this problem-solving strategy. This is a good place to start. If you look at a problem, you're like, I don't even know what to do. Do this. Draw a picture. Collect some information. Figure out, like, what does the problem tell me? Convert things if you need to convert things. Do any pre-calculations. Like maybe you can calculate something that's not the answer, but will help you get to the answer. And then solve. I like that step. So, like, oh, if I could have just started with that one, that would have made this so much easier. No, but at that point, you look at the relevant equations, right? Equations that are relate to the situation that you're talking about. So you can identify what kind of problem is this. That's going to matter more when we have lots of different kinds of problems, right? Is this an energy problem? Is this a momentum problem? Is this a kinematics problem? Is this a dynamics problem? Is it two of those butted up against each other? We'll see that. Okay, so let's keep going. So we drew a picture, and now we're going to collect information. So what is given to me? Well, I know there is a delta x of 5 meters that's associated with a delta t of half a second. Right, and then I know there's another delta x, so I could call this like delta x1 and delta t1, and then there's another delta x, call it delta x2, of 15 meters, and maybe that's all I know. And I think there's a step that I didn't include. Did I not include this? Yeah, I should have included a step. I think right here, or maybe right here. And that step would be this. Identify what you're solving for. That's not how you make a U, or sorry, a Y. How to make a U even. Identify what you're solving for. That's important. Where are we? Here. Because that's going to guide us, right? So find delta t2. Some of you already know what the answer is, and that's fine. Again, mostly the point of this problem is to help us think about this strategy, this problem-solving strategy, because not every problem is going to be as easy as this. Sorry. Okay. So we're going to have to make an assumption here. Let's assume that this is constant velocity motion. Assume constant velocity, right? Why do we assume that? partially because that's the simplest way to think about this. Also, I don't have more information to make any other kind of assumption, right? Realistically, the ball is going to slow down as it's moving, but I don't have enough information to know how it's slowing down, right? So this is a good place to start. So let's assume constant velocity, and I have a constant velocity equation, right? I actually only have one constant velocity equation. By the by, I posted the equation sheets, all of these equation sheets onto, there we go, Canvas. These are the equation sheets that would go along with our exams. So the first exam is is chapters 1 through 3. This is the equation sheet for that exam. So there's a list of equations. They're not separated into, like, they're not labeled by what they're associated with, but if you're familiar enough with them, you know this is the only equation for constant velocity. These are equations for constant acceleration, which we'll see, you've watched a video about, and we'll talk a little bit more about in a minute. And these are for free fall. This guy kind of goes with free fall. Okay, so these are not the ones we can use, though. This is the only equation we can use if we're assuming constant velocity motion. That's great. So now I don't have to choose among a bunch of equations. I just have the one. So let's go back and think about a problem, an approach to finishing this problem. Which one are you? There you go. And nope, we're in chapter 2. And here. Okay. Okay, we are so close, you guys. So the equation that we have is, it's really V equals delta x over delta t. And if we're assuming constant velocity, that's the same whether we do x1 and t1 or x2 and t2. So now you can kind of see, oh, you could do a proportion for this. You could do a cross multiplication, but that's not how I'm going to do it. I think I'm going to solve for velocity. That looks even less like a V than what I usually make. There, solve for velocity, and then we'll solve for that delta t2. Okay, so V is delta x1 over delta x2, sorry, delta t1, delta x1 divided by delta t1. Maybe later on the screen. So that's 5 meters divided by 0.5 seconds, which looks like 10 meters per second to me. All right, and then finally, I can use that same equation again for a different delta x to find the other delta t. But I really did run myself out of space. So let me go up here. I'll just use a little bit of the space. Oh, no. Right, so V equals delta x2 divided by delta t2. That V is 10 meters per second. The delta x is 15 meters, and I'm looking for delta t2. Right, so then I can algebra that a little bit, and I should get 1.5 seconds. Questions about that? Again, I think that's pretty straightforward. Not every problem will be quite this easy. The last step, though, of solving any of these problems is, does my answer make sense? Is that a reasonable answer? And I would say, yeah, 1.5 seconds for a soccer ball to go 15 meters is probably pretty reasonable. It's going pretty fast. 10 meters per second is pretty fast. I think I may have made up these numbers years ago. So it's pretty fast, but it's not totally unreasonable. I will say, we made this assumption, right? Let's use yellow. I don't use yellow very often. We assumed the velocity was constant. And in reality, it's probably getting smaller. So our time here is probably an upper limit, right? So even though, because I had a student ask me this question last year when I was teaching this course, said, if we know that this is wrong, why are we even doing it, right? And the answer is, well, because this gives me an upper limit on the time, right? I don't think it was this specific problem he was asking about. And that's a valid question. If our model isn't really right, if the velocity really isn't constant, what good is it? And again, the answer is, it gives us a good estimate. It gives us an order of magnitude for sure. Okay. Yeah, we good? All right. Okay, let's move forward. This is something a little more different. It'll actually be a little more the same, but that's okay. I want this space back. Okay. So let's do a couple more, maybe two more of these kinds of problems. Example, you know what? That's not what I'm going to do yet. Example 11, I don't know what it is. It says, draw the motion diagram for a car coming to rest at a stoplight. Draw the motion diagram for a car coming to rest at a stoplight. So, okay, motion diagram is like a straight line. We could give it some tick marks, but those are bad looking, so I'm going to make them go away. I don't care too much about the tick marks here because we're just thinking about this qualitatively. So when a car comes to rest at a stoplight, what is it doing? It's slowing down, right? So the points should start far apart, and then they should get closer together and closer together until it comes to rest. So that's some version of a car coming to rest at a stoplight. This is maybe what my dad would call a driver's ed stop. He was a driver's ed teacher. So if your parents taught you to drive, imagine them teaching all of your friends as well. It was okay. But this was a driver's ed stop, right? You're slam on the brakes right at the end. So plot position versus time for this motion. So what does position versus time look like for this? Well, so this is now acceleration, right? This is now changing velocity, which we call acceleration. And hopefully if you watched the video, you saw this delta V over delta T. This is technically average, again, average acceleration, but in this course, we're only going to talk about constant acceleration. So this is exactly true for all of the problems that we'll do. So we could plot this, plot position versus time. Let's draw. Now we could do this. So here's time and here's position. And let's have a start at the origin. Why not? And initially we're going kind of fast, right? So it's going to be a big slope, but then the slope gets smaller, right? So these first 2 points would be like these first two. Why aren't you making marks? There we go. And then the next 2 points, like this one to this one, is a little smaller. So that could be like right here. And the next two would be a little smaller still until we're pretty much stopped. So that would look kind of like this. Right? What does velocity versus time look like for this? Again, it's the, there's a V and there's a T. It's the slope of position versus time. Is that going to work? Yeah, I'm a little off. That's a little. So it's going to start big, and it gets smaller as you go. It goes to 0 eventually. Right, and this really is a straight line. I did the derivation in the acceleration video. This really is a straight line. And position versus time really is a parabola. Do I have, no, I'm gonna put it in here at the end. Let's plot acceleration versus time. So here, the slope of position versus time is velocity. Turns out the slope of velocity versus time is acceleration. So what is that slope? What's the sign of that slope? Anybody? What's the sign of the slope of acceleration?
Negative.
It's negative, yeah, which means I need to move this down like here. And it's constant. That's great. Okay, so there's our negative acceleration. Often when acceleration and velocity point in opposite directions, we colloquially call that deceleration, right? Slowing down. But an object that is changing velocity is accelerating. Even if it's slowing down, we call that acceleration. All right, so again, in physics, in a scientific sense, anytime velocity is changing, that's acceleration. Okay, so we have equations that describe these. Again, I derived them in the video. I will just show them to you here. So they are the kinematic equations, right? These three equations describe what we just drew, right? In fact, velocity as a function of time. This is the equation of a parabola. I did say velocity. I meant position as a function of time. This is the equation of that parabola. This is a straight line, velocity as a function of time. And this one doesn't depend on time, so it doesn't relate to our, what do you call it? It doesn't relate to the graphs we just drew, but it is, if you take these two equations, the first two equations, and plug them in to each other, one into the other, you can get the third equation. Okay. So these are only true, these equations are only true for constant acceleration motion. So let's do, we got 9 minutes. Let's do one of these examples, and then maybe I'll talk about free fall just a little bit. Come on, man. Okay. Okay, how are we doing? Are there any questions? All right. Lonely Screen wants to know if I will subscribe. Answer still no, buddy. All right. So the 2002 Lingenfelter Chevrolet Corvette can go from 0 to 60 in about 2 seconds. I assume that it could in 2002. Maybe it can't anymore. This was the record at the time that I first started teaching, and I haven't bothered to update this since. So this may not be the record, but I didn't say it's the record in the handout, so we're just going to say this is true. So we could ask, what is the acceleration during this trip? So we're going, let's draw a picture. How do you draw a car? I don't know. How do you draw a fast car? I don't know. It's like sleek, right? Sure. No, that looks like a UFO. That's fine. So here's our car, and it's going from 0 to 60. Where are my dots? There they are. So V initial is 0, right? And V final here is 60 mph. And I'm going to assume that this motion is constant acceleration. Probably not entirely true, but not a terrible approximation. Okay. What else do we know? We know a time. We know that delta t for this motion is 1.97 seconds. Okay, so we ask, what is the acceleration during this trip? And we're also going to ask, how far does it go? So how far is a delta t? Sorry, delta x. So I could label that. There's my delta x. So we're kind of identifying. We drew a picture. I'm kind of gathering what I know by drawing it into the diagram. And I'm identifying what I'm solving for. I guess I could do this. A equals question mark. Delta x equals question mark. Is there another part to this? How fast is it going after 8 seconds? So that's another time interval. So this gives me another delta t. And I'm looking for a v final after that, but we'll get there. or maybe we'll skip that part. We'll see. Okay, so acceleration, again, if we're assuming it's constant, we can just use the definition of acceleration to solve for this. So A equals V final minus V initial divided by delta t. V initial is 0, which is nice, but V final is in miles per hour, and I really prefer that to be in meters per second. I think I did that conversion last time, miles per hour to meters per second. Turns out V final, 60 miles per hour is like 26 meters per second. I'd like to find the other. I have the solutions, but they are not on that screen. I covered them with my, here we go. Hey, I don't even have to draw anything if I do this. I can just show it to you. See, I drew the Corvette differently here. Let's just find this here, 26.8 meters per second. Yeah, we'll go back and I'll do it live. So 26.8 meters per second divided by 1.97 seconds. I should have moved that screen somewhere else. I think it turns out to be, what, yeah, like 13 point something. That's 13.6 meters per second, or meters per second squared. Okay, how far does the Corvette travel in this time? So I would look at my kinematic equations, right? They're up here. Let's make some of these go away. There's my kinematic equations. I'm looking for delta x, and I know V initial and V final. I also know the time. So it looks like I could probably use a couple of these, either one of the first one. Nope, first one doesn't give me an x, but I could use the second one or the third one. You guys see that? You could highlight what you want to find, right? I'd like to know delta x, so that's here. Delta x is a combination of those two things, x final minus x initial, but x initial is 0, or I can call it 0. So either one of those should work. Oh, lost my screen. Come back. Come back. Or not. It's trying to connect. No, that's fine. We'll give that. Okay, that's fine. You know what? I've got 2 minutes left in lecture, so let's just ask again, because I care. Do you guys have any questions? So let me say this. I have, probably 3 other examples here, plus an example about free fall. So free fall is just a special case of constant acceleration. So we can rewrite the kinematic equations in the y direction with a specific acceleration, right? The acceleration due to gravity is 9.8 meters per second squared down. And watching me do that live that's fine. Like, I say some stuff that I hope is meaningful, but the best thing you can do is practice, right? And to that end, we have discussion sections for this class. One of them starts in 11 minutes. If you're in that section, the other one is tomorrow at 4 o'clock Eastern. So join that discussion, right? And what you'll do is I'll break you into groups, and you'll work some, yes, I know. You'll work some of these practice problems, right? The first one is chapters 1 and 2. You're not gonna have time to work all of those in 50 minutes. I would suggest you probably work the chapter 2 ones, because that's a little trickier. Okay, so I think that's good. We good? Okay, so I'll see some of you in 10 minutes and the rest of you tomorrow at 4 o'clock. So, thanks, guys.
Thanks.
There's some chat.